AI in Munich, and she will present the cool model named Titan, a multimodal whole slice foundation model for pathology, which is trained on histopathology images and clinical reports. Looking forward.
Thank you. Welcome to the talk on Titan. We go back to the health domain with that. And with this project, we're trying to find representations for these tissue sections on microscopic glass slides, so similar to what we saw in the first talk. And the goal is to map these representations then to clinical endpoints, so diagnoses, treatment response, or other biomarkers. And the challenge here is that these digitized whole slide images really have very large tissue scales. So as you see here, you can zoom into the tissue, and in order to process them by a computer, you really need to patch it into these tiny images, but you end up with thousands of these images for one whole slide image sample. So the normal procedure is to tile these images into these smaller patches, to then compress the information that is contained into these patches through patch encoding in features, and then to aggregate the multiple thousands of features that you have for a clinical endpoint, and this is done by supervised learning. So typically, this gigapixel image has these multiple thousands of images, which are ideal for self-supervised learning to train them on that. So this is done. In fact, we have these patch-level foundation models. We have seen them over the maybe past year a lot. So we consider these representations as solved in a way, but they only encode a local context. So they don't have a really understanding of the entire tissue that they see, and the feature aggregation is always trained for one specific task, and this task has also no global context of the entire slide. So we are really lacking a model that finds a representation from the whole slide image to one clinical endpoint. And in the supervised training, we usually have way larger number of parameters per training samples. If we, for example, have only a clinical cohort of 500 samples for one particular biomarker. So what we want to do in this project is, I hope this will not be the quality of the images throughout. So we want to bring the patch-level self-supervised learning to the slide-level self-supervised learning. So we look at these patch encodings that we have and rearrange them spatially so that we have these regions, and then train a self-supervised learned model on this feature space, on this region that we have. We do this on a large data set of 340,000 slides, and we also do it in a multimodal training where we use captions that we synthetically generated describing the content in a smaller image region, and then finally also the clinical reports that we have available for 190,000 of these patients. So the first step is very similar to a Dino or iBot model, where we take these feature regions and we crop global and local regions out of it. We add frozen feature augmentation because it's in the feature space and not in the image space anymore. And we also use alibi as positional encoding, where we can scale from train on short contexts like these regions and scale to the whole slide image in the context at inference. And the multimodal pre-training is done in 2 stages. So first we train on these regions of interest with the captions. We use COCA for this, so it's an extension of CLIP where we also generate the captions. So in the end, after stage 3, where we train this on clinical reports, we can also generate pathology reports from the whole slide images that we see. And we show that this pre-training in 3 stages is more efficient than the models that are available for that. There are 3 models out there trained on smaller and on larger data sets, and we evaluated on public data sets trained on these regions that our model learns more efficiently with less data already, and also on whole slide image scales where we tested on TCGA, which is the largest publicly available data resource, and then also on an internal data set which involves more rare cancers as well, and then also a brain tumor data set which is called eBrains, which is very challenging with rare diseases. These are also the 4 core tasks, so where we evaluated our model mainly on, but we also included more evaluations. So this is now the average on these 4 core tasks of our model on the left, TITAN, and we see that in linear probing, which is basically just fitting a logistic regression out of the slide encoding that we now get, we are outperforming the existing models. But the nice thing is now that it doesn't depend on this linear probing evaluation. We also see that we trained a good slide encoder by comparing it to other evaluation schemes. So one evaluation scheme to test the effectivity of our slide encoder is to test whether the mean aggregation of all patches, which would be the easiest aggregation, actually is improved over by our model, which is not the case for all models. For example, GigaPath cannot outperform their mean aggregation. And we outperform the mean aggregation. We also outperform supervised models that are trained on the task specifically. And we also provide a good or like a checkpoint where we can fine-tune and achieve a better performance on a specific subtask. This is in comparison to randomly initializing our aggregation, which is also not the case for all models. And then what else can we test on? We tested it on morphological classification tasks, on grading tasks, and on molecular classification and survival prediction, and our model can handle all of these where it shows the best improvement, so to say, on morphological classification. Here's the overview of a subset of tasks, and we hypothesized that this is because we trained it in this first step vision-only training, and then contrasted with the reports and the descriptions which describe the morphology in our stage 2 and stage 3 training. And as seen in a previous talk, we also tested few-shot learning, so by varying the number of training samples that we had available, also shown on these 4 tasks. And we also looked at the slide representations that we have in latent space. So these are the previous models that exist. This is the TCGA dataset that I was referring to earlier, and you see the cancer subtypes here, and our model really has the nicest clustering with our vision model in the one before of all these models. And what can we do with this slide embedding now? We can also say, for example, we have a database of clinical challenging cases. We have an embedding of a rare cancer case, and we can now retrieve similar cases in a database of other cases. And we collected for that a database of rare cancers in the hospital where we trained this on, but also have a public database on that. And we see that our model retrieves these tasks the best, and also compared on these 4 core data sets. And the nice thing with this multimodal alignment to pathology reports is that we can now also describe our images and do zero-shot classification. So if we're interested in a certain property, we can just, in the latent space that is aligned, measure the distance of our sample to different descriptions and get a classifier for tasks that is almost on par as the supervised performance on these data sets. For example, we have the eBrains data set here, the performance is on par almost, and renal clear cell carcinoma and the other data sets. And finally, 2 other And this is some architecture ablations, which we can discuss later, but another retrieval task is now also this report to slide retrieval. If you have a clinical condition and you're searching for similar slides, and you can really, it's in a way like consulting another pathologist, and you can consult the clinical history before. And finally, the model can also generate reports, which we didn't evaluate clinically, but we evaluated it on measuring the semantics. And the next step would then obviously to test this in a clinic, whether the descriptions contain everything we want to see. And this brings me already to the end. So in summary, we have seen in the script, we have H&E slides, we have IHC, so immunohistochemistry information, and contrasted them in a multimodal way with captions and reports. And we saw that this three-stage training with vision-only training in the first step and then vision-language training is more effective than previous recipes and yields better representations in the end. And this would have not been possible without my co-authors, Tong, Andrew, and Richard. And I also want to thank Ting Ying, who's my supervisor at Helmholtz Munich, and Long and Faisal, who are the supervisors at Harvard Medical School, where I did the project in an internship in the past year.
Thank you so much for this presentation. Questions? I see someone. Yes.
Hi, Sophia. Amazing talk. I have a very questions about the metric that people have been using, especially in the caption generated from histopathology. Do you think it makes sense to maybe do some research and come up with new metrics to evaluate the prompting or the text generation for pathology, because it's such a complex text as compared to simple computer vision?
I can imagine that like BERT scores also with clinically specific models, right, that really understand, are domain specific like BioGPT, and you measure there the embeddings could help. Yeah, but there are already papers who investigate that. We just use these standard metrics in this paper, but we definitely need to work on that. Otherwise, we cannot evaluate how good our reports are. Yeah.
Very good. Thank you.
I would have a question because whole slides from pathology tend to have different sizes, right? If you have a stance or an entire dissection, is this a problem for the model, that sort of your slides can vary significantly in size?
Yes, that's also one reason why we do this multi-stage training. So the first and largest part of the training process is this region training, where we like on GPU size, we have a similar size as normal self-supervised training, because we only have these 16 by 16 tokens in the feature space. And then for the pathology report training, we need the entire slides. So we only have very small batch size, and that's why we only use it basically as a high resolution training at the end of our model. Yeah, that's a challenge.
And we have one more question here.
Yeah, thank you. Thank you, Sophia, for the great talk. I have a question regarding molecular multimodal models. I think you already have a publication about that, and I was thinking, what do you think is the pathology going towards? Is it like integrating spatial transcriptomics with the histopathology data and the pathology reports? What do you?
Yes, definitely. What I mentioned in the one overview, where our task is basically our model is basically the best at, is that we saw here. This is it's better at morphological tasks, because we really focus in the pre-training on the morphology understanding, because we have morphology descriptions and captions, but we don't really give the model molecular information already in this project. But we also have another project where we contrasted it with molecular information, and there we see the biggest gain, obviously, on the molecular tasks. So ideally, we combine all these information and we bag all information that we have into the model. Finally, yeah, we really saw, for example, if we have in the clinical reports IHC results, so the molecular test results, we really saw if we include them that the performance on the molecular task increases as well. So, yeah.
Okay, yeah, thank you. Yeah.
Yes, thank you, Sophia.